No matter how peculiar or even artificial the concepts of dark matter and dark energy may seem to you, they are deeply integrated into our standard cosmological model. As much as you might want to dismiss them as inventions, you cannot ignore the fact that all the ordinary matter in the universe, composed of protons, neutrons, and electrons by itself, cannot account for the full range of gravitational effects observed by astronomers. For now, scientists cannot avoid including invisible forms of matter and energy in the model of the universe, which first, produce effects consistent with observations, and second, make the universe align with the predictions of our best theory of gravity. Still, the hypothesis that everything around us is built on something invisible, which emits no energy, cannot be detected in laboratories, and affects the world only through gravitational attraction. This hypothesis, while widely accepted, nonetheless compels the search for alternative explanations. Since I recently came across one intriguing alternative hypothesis about dark energy, I have a feeling you might find it equally interesting. First of all, we should discuss the principle underlying all modern cosmology, our understanding of the universe as a whole. In fact, this principle was first articulated in the 16th century by Nicolaus Copernicus, who argued that Earth does not occupy a special place in the universe. This assertion, far from obvious at the time, is now beyond dispute and has evolved into something broader, what we call today the cosmological principle. It states that no matter where you are in the cosmos, you will always observe the same large-scale structure. In other words, the universe is homogeneous, and this remains true regardless of the direction you look, meaning it is isotropic. Today, with entire 3D maps of galaxy distribution in the universe, this appears to be a plausible characterization. However, it should be noted that the idea of a homogeneous and isotropic universe originally emerged as a hypothesis. This assumption was necessary when scientists aimed to create a workable model of the universe consistent with the revolutionary general theory of relativity. As you know, according to Einstein's idea, the geometry of space-time depends on the distribution of matter and energy within it. However, Einstein's equations are nonlinear and difficult to solve in general. To simplify this task, Alexander Friedmann proposed the assumption that the universe is homogeneous and isotropic, meaning it is uniform and consistent in all directions. This assumption allowed him to solve Einstein's equations and describe physically grounded models of the universe that align with the general theory of relativity. These are the models you are familiar with. The universe either expands or contracts, and its geometry can be open, closed, or flat. These models, in fact, enabled the prediction of the universe's expansion, later confirmed by Edwin Hubble. Subsequent scientists found solutions to Einstein's equations that also correspond to the expansion of space, and the metric model known as the Friedmann-Lemaitre-Robertson-Walker model became the mathematical framework of standard cosmology. Over time, advances in astronomical observations confirmed the even distribution of galaxies on large cosmic scales, supporting Friedmann's hypothesis. Finally, after the discovery of the cosmic microwave background radiation, the homogeneity and isotropy of the universe on the largest scales were definitively accepted and are now the foundation of modern cosmology. It is important to note that the Big Bang cosmology has proven to be quite resilient. It readily adapted to new and strange discoveries, such as dark matter and, most critically, dark energy. In 1998, the scientific community was shocked by the results of distance measurements to Type Ia supernovae, which turned out to be farther away than expected based on the expansion of the universe. Cosmologists learned that around 5 billion years ago, the expansion of the universe began accelerating. A puzzling finding, given that the universe was known to be flat, and the gravitational attraction of all matter and energy should have gradually slowed down the expansion. To reconcile the accelerating universe with flatness, a balancing factor was required. So a new parameter was added to the equation, the cosmological constant, originally proposed by Einstein. By including this coefficient, cosmologists once again arrived at a flat universe, albeit one expanding with acceleration. And that is how we arrived at the concept of dark energy, a phenomenon with a repulsive nature whose underlying cause remains a mystery. Of course, not everyone is satisfied with this turn of events, and the temptation to find alternative explanations persists. Some scientists aim to measure the distances to supernovae with greater precision, hoping to uncover statistical errors in earlier measurements. Others, however, conduct new analyses and repeatedly confirm the existence of accelerated expansion. Some propose revisiting the very theory of gravity, suggesting that its laws might be incomplete on cosmological scales. Yet another intriguing way to dispense with dark energy is to abandon the assumption of the universe's homogeneity and isotropy. Indeed, this may sound somewhat heretical, as the distribution of galaxies in three-dimensional space and, especially, the cosmic microwave background map strongly support the cosmological principle. However, there remain questions about the extent to which local inhomogeneities can be ignored. It is known that the tiny temperature variations in the cosmic microwave background reflect density fluctuations in the early universe, which served as the foundation or template for the subsequent distribution of matter into a large-scale structure. The modern distribution of galaxies and galaxy clusters was imprinted by these variations. Over time, as the universe expanded and evolved, a network of high-density regions, superclusters of galaxies, gradually formed. Between these regions lie vast voids, or cosmic voids, where the density of matter is significantly lower than average. While not entirely empty, they contain sparse gas and isolated galaxies. Their sizes are staggering, tens to hundreds of millions of light-years. The largest voids, those exceeding 160 million light-years, are thought to constitute around 40% of the universe's total volume. Add smaller voids to the mix, and together they make up more than half of the observable universe's volume. Thus, while matter in the early universe was distributed almost uniformly, over time, gravity created distinct structures, and the distribution of matter and energy became far less uniform. This raises an intriguing question. How do these inhomogeneities affect the expansion of the universe? Of course, the modern, widely accepted cosmological model, lambda CDM, acknowledges the existence of inhomogeneities in the universe, but assumes that their impact on large-scale average expansion is negligible. However, an alternative model of inhomogeneous cosmology suggests taking this effect into account. The idea is that gravity influences the expansion of space differently depending on where you are, whether in a galaxy cluster or within a giant void. Within clusters, where the concentration of matter is high, expansion occurs more slowly because, according to general relativity, the rate of expansion is influenced by the mass of matter and energy present. Thus, inside galaxy clusters, the curvature of space is greater and expansion slows down. In contrast, in voids where matter density is at its lowest, space expands more rapidly. Since voids make up a significant portion of the universe's volume, they could affect the average expansion rate, creating the illusion of acceleration. In this context, no unknown form of energy is required. The observed accelerated expansion could result from the uneven distribution of matter in the universe. Interestingly, this model provides a straightforward explanation for why the acceleration began to affect the universe only 5 billion years ago. This is a controversial point, as if dark energy had been active immediately after the Big Bang, the universe would have expanded so rapidly that galaxies, and consequently life on Earth, would not have formed. In contrast, in the inhomogeneous cosmology model, this is not an issue. 5 billion years ago is simply the time when matter had aggregated enough for voids to dominate and begin influencing the overall expansion effect. There's another, perhaps even more intriguing interpretation of this model, based on one of the strangest effects of general relativity: time dilation. This hypothesis is known as timescale cosmology and was first proposed in 2007 by cosmologist David Wiltshire. Contemplating the accelerated expansion of the universe, the author suggests accounting for the effect of clocks ticking differently depending on where you are. According to the principles of relativity, observers near massive objects and those far from them experience time differently. In other words, within galaxy clusters, an ideal clock ticks more slowly than in regions with low matter density, such as voids. Thus, a clock inside the Milky Way would operate much more slowly than the same clock within a large cosmic void. As a result, more time has passed in voids than in clusters, meaning the universe has expanded more in those regions. The average effect of the expansion rate across all space creates the impression of accelerating expansion as voids dominate. So, it sounds intriguing, doesn't it? But what about the evidence? David Wiltshire, the author of this idea, along with his team, tested the hypothesis by measuring distances to supernovae and comparing their model to the standard lambda CDM model. The results were inspiring, as timescale cosmology seemed to fit the observations just as well as the standard model. Later, another group of scientists refuted these findings by testing the alternative model on a larger sample of supernovae. However, proponents of the alternative hypothesis responded with a new study, challenging the critics' data and citing systematic errors. A classic scientific story. In reality, despite its elegance, timescale cosmology undoubtedly has several shortcomings. It is somewhat mathematically more complex than lambda CDM because it incorporates a new parameter, the proportion of voids in the universe. Moreover, it is quite challenging to model, requiring sophisticated simulations to show how inhomogeneities influence the average expansion. Finally, proponents of this model would need to work hard to reconcile it with the cosmic microwave background (CMB) map, which is very well explained by lambda CDM. As a result, due to its relative complexity and immaturity, this model still has few adherents. Nevertheless, I chose to make this video for a reason. On December 19, 2024, a new study was published in which supporters of the alternative hypothesis made another attempt to demonstrate the advantages of their model. This time, the authors analyzed what is arguably the largest and most precise dataset of observations, known as Pantheon Plus. It includes over 1,600 recorded Type Is supernova events across a wide range of redshifts, meaning at various distances from us. This dataset is characterized by more accurate measurements of brightness curves, better calibration, and minimization of systematic errors. For the first time, the authors decided to test the timescale model against such a large dataset and compare it to lambda CDM. The results they obtained were quite interesting. At relatively low redshifts, that is, within the local cosmos, timescale cosmology demonstrated a strong statistical advantage over lambda CDM. This indicates that the impact of the inhomogeneous distribution of matter, namely the influence of voids, could be significant in explaining the universe's expansion on small scales. At medium redshifts, the scientists found that both models were statistically equivalent and could explain the expansion equally well. Finally, for higher redshifts, that is, on larger scales where the universe appears more homogeneous, timescale cosmology still maintained a slight advantage over lambda CDM, or at least that's how the authors interpret their results. Notably, they are cautious in their conclusions and emphasize that their findings look promising but still require more precise data, especially at low redshifts, where the impact of matter inhomogeneity is most noticeable. Furthermore, the authors acknowledge that their model does not necessarily reflect the true nature of dark energy, but their main message is that over-focusing on a single theory can be detrimental to science. Of course, each alternative hypothesis is considered alternative for a reason. It falls short in many ways compared to the standard cosmological model, which is simple, comprehensible, and appears to align well with observations. The concept of dark energy, whatever it may be, whether a cosmological constant or some exotic form of energy, is an integral part of lambda CDM. Therefore, you can rest assured that it remains the leading explanation for the accelerated expansion of the universe. But it is certainly the weakest link in our current understanding of the cosmos. There are so many questions about it and so few answers. Particularly striking is the discrepancy between the predicted strength of dark energy and what we actually observe. Quantum field theory, which describes dark energy as vacuum energy, calculates a value that exceeds the observed one by a factor of 10 circumflex 20. If dark energy were indeed this strong, even atoms would be torn apart by its effects. This is simply the greatest mismatch in history between theoretical predictions and observations. It's clear that we are fundamentally missing something crucial in our understanding of this phenomenon.